This is my Calculus 1 course. Today we're going to learn differential calculus. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In previous courses, we learned the different forms of linear equation. We have slope-intercept form, point-slope form, and standard form. And we also learned how to measure the steepness of a line using this value down here, which we call the slope of a line. We use this formula if we have 2 points on the line. But if we have one of either these two equations here, either these two forms, we can see the slope just by looking at the equation. And over here you see we have slope-intercept form. So we can see the slope just by looking at that equation. The slope of this line is 2. But what does that mean for the slope of the line to be 2? Well, we can think of the slope as a measure of the steepness of the line, but we can also think of it as a measure of the rate that the y values on the graph are changing as the x values change. So let me show you what I mean. Let's choose a point, say here, 1, 1. And let's move a certain distance horizontally. So I'm just going to move out 1 unit horizontally. And then let's see how many units we have to move up to get back to the line. So you see we move up 2 units vertically. If we move 1 unit horizontally, we move 2 units vertically to get back to the line. And so what we do is we divide these numbers. We divide 2 by 1. Remember, we call this rise over run. Rise divided by run. And this number is a measure of not only the steepness of the line, but also how rapidly the y values are changing as the x values change. It's the rate of change of the function. Now, it's very important to understand, when we say the rate of change of the function, what we mean is the rate of change of the y values of the function. The y values are considered the values of the function because they're the outputs. Given given the inputs, the y values are the outputs of the function. So the function changes 2 vertical units for every 1 horizontal unit. Now, it doesn't matter where you are on the graph. Let's choose this point here, and let's choose this point here. The change is the same. If we move 1 horizontal unit, we have 2 vertical units to get back to the line. So the rate of change is the same anywhere. And if we choose a point down here and a point up here and measure the rate of change, we still have double the number of vertical units that change in comparison to the horizontal units. So 6 divided by 3 is still 2. So again, anywhere on the line you have the same rate of change. And so we say that the rate of change of this function is constant. It's always 2. But what if we go to a curve? How do we measure the rate of change of the function as the x values change? In other words, how do we measure the rate that the y values of the graph are changing as the x values change? Well, obviously it's a little more complicated, but let's use the same technique to measure the rate of change of this function. Let's choose these 2 points here. And let's move 1 horizontal unit, and let's determine how many vertical units we have to move to get back to the graph. Well, that's going to be obviously 1 vertical unit. So if we want to measure the rate of change, we divide these numbers. 1 divided by 1 is 1. So the rate that the function is changing from this point to this point is 1 vertical unit for every 1 horizontal unit. But let's pick up where we left off, and let's now measure the rate of change between this point and this point up here. So we're going to go out one horizontal unit and see how many vertical units we have to move up to get back to the graph. And you see now we move 3 vertical units for this one horizontal unit. So I'm letting the purple numbers be the horizontal movement and the green is the vertical. So it's different. It seems as though the rate that the function is changing is now different. The y values are changing more rapidly for every one horizontal unit. So now let's start where we left off, and let's move out the same horizontal distance, one horizontal unit, and let's see how many vertical units we have to move to get to the corresponding point on the graph. And now we move up 1, 2, 3, 4, 5 units. So the rate that the y values are changing, again, the y values are increasing more rapidly. So again, this is a much more difficult situation to analyze compared to a linear equation, because again, the rate that the y values are changing at any place on this line the rates are all the same. They're all 2. The rate that the function is changing is constant everywhere on the graph. But that's not true for this graph. We can see. Well, it turns out that the rate that the function is changing is different for every single point on this graph. This graph has an infinite number of points. You can choose a point here, a point here. You can get a microscope and you can zoom in an infinite number of times, and you're going to find more and more points. There's just an infinite number of points on this graph, and every single point on this graph has a different rate of change. If we measure the rate that the y values are changing, so the rate of change of the function is different at every single point on the graph. That's not true for every function, but for this one it just happens to be so. So what we're going to do is we're actually going to find the rate of change of the function at one point on the graph, and we're going to call that the instantaneous rate of change. And the reason we call it the instantaneous rate of change of the function is because if you move a small amount to the right or to the left, then the rate would be different. The rate of the function would be different. It doesn't matter how small of a movement it is, the rate changes. So at one particular point, if we can somehow find the rate of change of the function at that point, that's called the instantaneous rate of change. So in order to demonstrate, let's go to a curve that is vertically compressed, because it's going to be easier for us to see. So let's say that we want to measure, or we want to find the instantaneous rate of change of the function at a particular point. What we're going to do is we're going to choose another point on the graph, and then we're going to calculate the slope of what we call the secant line. So the secant line is the line that goes through these 2 points. And the slope of that secant line is what we call the average rate of change in this interval here. We just define the slope of the secant line to be the average rate of change. That's a definition. So it's just defined as the average rate of change of the function between these 2 points. So we're going to calculate the slope of that green line. Again, it's called the secant line. But then we're going to move this point down closer to the other point. And then we're going to measure the slope of the secant line again. Now we have a new secant line, but we're going to measure the slope of that green line again. And then we're going to move that point even closer. And then we're going to measure the slope of the secant line between those 2 points again. And if we keep doing this, bringing this point closer and closer and closer, what we find is that the slope of the secant line approaches a number. And whatever number that the slope of the secant line is approaching, that number is defined by mathematicians as the instantaneous rate of change of the function at that point, that purple point. So eventually, when the point gets right on top of the other point, we have a new line that we call the tangent line, the line tangent to the curve at this point. And the slope of this line is that number we're looking for, the instantaneous rate of change of the function at that purple point. So that is differential calculus. That's how differential calculus works. Now notice that we said that the slope of the secant line is approaching a number. So as the dot gets closer and closer and closer, the slope of the secant line is approaching a number. Remember, limits are all about approaching a number. So it should be no surprise to you that we're going to use the concept of limits to help us find the slope of the tangent line, which is the instantaneous rate of change of the function at that point. Okay, so what you're going to find is that the concepts in calculus are, well, a lot of them are not really that difficult to understand. A lot of the concepts in calculus are actually not really that difficult to understand, but the notation can be confusing. And for any math course, the most difficult part of the course is learning the language, learning fluency in the language. And so this course is no different. The language can get a little confusing, and that's particularly true for calculus. And now we're going to talk about that language that we have to learn, and we're going to have to use function notation. Function notation, if you recall, I mentioned in previous courses that function notation can be very confusing. And you're about to see that right now. So this may be a little confusing, but if you don't understand everything that we show you here in this picture, again, it's just going to take a while to learn the language. But if you don't understand everything that you see here, that's okay. We can always go back to this. But we're going to use function notation to come up with the language that we use to notate all the concepts that we just talked about. So we have 2 points. We have a purple point here, and we have a purple point up here on this red graph. And the coordinates of this first purple point are x, comma, f of x. Remember, f of x is just the y values of the graph. So if your x value of this point is x, then your y value is f of x. Again, I know that's confusing, but that's just the notations mathematicians use, so you have to get used to it. Now, what we're going to do is we're going to find the coordinates of this point up here. H is a number that we add to x. So we're already starting with this x value here, but we're going to add h to that x value. And so the x value of this coordinate up here is going to be x plus h, because you have to move out this yellow distance in order to get our x value of this point. The x value of that point is x plus h. Again, you start at x and then you add h units to get all the way over to here. So x plus h is the x value. If the x value of this point is x plus h, then the y value is f of x plus h. Again, I know that's very confusing. This is not multiplication. It doesn't mean f times x plus h. That's not what this is saying. This is function notation. I know that this looks confusing, but all it means is that if you plug in x plus h to the function, your output is f of x plus h. So that's the y value of this point. Again, I know this is very confusing. This is where calculus gets really difficult. It's just a language that you have to learn. So if you're a little confused by this, that's okay. Every student is confused by this when they first see this. But f of x plus h is the y value of that point, which means that this distance here is f of x plus h, because remember, y is the vertical distance from the x-axis to the point. So we learned in previous classes that the slope of a line is equal to this expression here if we have 2 points on the line, or the coordinates. If we have the coordinates of 2 points on the line, we can find the slope of the line given this formula. So we're going to use this formula to find the slope of the green secant line using those 2 purple points. But we're now going to use our function notation. The y value of this point up here is f of x plus h. So we're going to plug that in for y2. The y value of this point down here is f of x. So we're going to write f of x. Again, we're finding the slope of the green line using these 2 purple points. Then x plus h is the x value of that point up there. So we're going to plug in x plus h for the x value up there. And of course, x1 is x. That's the x value of this point here. So we're going to calculate the slope given that notation. Now notice that the x's cancel out in the numerator, and you're left with h. This expression that we see here is the slope of that green line, just using function notation. And I know what you're thinking. You're thinking, why are we making this so complicated? Well, again, this is just notation that mathematicians use to calculate the instantaneous rate of change. This is something you're going to have to learn. This expression is what we call the difference quotient. We learned this expression in my pre-calculus course. The difference quotient can be written in many different ways. This is just the way that we use in the calculus curriculum. And again, the slope of the secant line is defined to be the average rate of change of the function on some interval, and this is interval notation down here in green, x comma x plus h. You don't really need to pay attention to that. That just means we're talking about this yellow interval here between the 2 points. Okay, so that is the average rate of change of the function, and what we're going to do is we're going to bring this point up here down the graph closer to the other point, just like we did in the previous graphs. So notice that this point is now closer to the other point. We're moving it to the left. And so h, this orange h, is getting smaller. It's getting smaller and smaller. Look at that. See the orange h? It's getting smaller and smaller. That's how we bring this point up here closer and closer to the other point. So we're bringing it closer and closer, and we're letting h approach 0. And if we let h equal 0, then the 2 points meet, and the green line now becomes the tangent line, what we call the tangent line. So the slope of this tangent line is what we're looking for. That's defined to be the instantaneous rate of change of the function at this particular point. And again, when we say the instantaneous rate of change of the function, we mean the instantaneous rate of change of the y values as the x values are changing. The problem is, in order for the points to meet, h has to be 0. Notice that x and x plus h are exactly the same because we're letting h equal 0. if we look at this expression, this is the slope of the green line. But if we let h equal 0, then we have f of x plus 0 minus f of x over 0. Again, we're letting h be 0. So now we have f of x minus f of x over 0, which is 0 divided by 0. So if we let those 2 points meet, the slope of the secant line now becomes 0 divided by 0. And 0 divided by 0 has no meaning. So we cannot calculate the slope of the tangent line directly. But we can find the value that we want, the slope of the tangent line. We just can't do it directly by letting h be 0, because we get 0 divided by 0. So what we're going to do is figure out what the slope of the secant line is approaching. Again, as we let h get smaller and smaller, the slope of the secant line is approaching a number, and we can figure out what value the slope of the secant line is approaching. And in order to do that, we're going to use a limit, because remember, limits are all about finding a number that an expression is approaching. So we're going to find the limit of this difference quotient, the limit of the slope of the secant line as h approaches 0. So this is very fancy notation that simply means we're finding that number that the slope of the secant line is approaching as the purple dots get closer and closer together. And this expression here is the slope of the tangent line. That's what we're looking for. And we call that the derivative. It's the derivative of the function. So instead of calling it the slope of the tangent line, we call it f prime of x. You see this apostrophe here? That we pronounce that f prime of x. So this formula is what we define to be the instantaneous rate of change of the function at a particular point. It's the slope of the tangent line, if you want to think of it in geometric terms. Now, this formula is the most important formula in the entire calculus curriculum. The entire curriculum is based on this formula. So we're going to take a picture of that, but before we move on and actually start the class, I just want you to know that defining the tangent line is kind of a difficult thing. We define the tangent line as the line that touches the graph at one place, but that definition is not very good, because technically the graph, could turn down like this, and then it would touch the tangent line in more than one place. But you can just think of the tangent line as the line that touches the graph at only one place around this point. If we tried to get more specific, then we would go into what we're about to talk about, and that would get a little confusing. So again, you can just consider the tangent line to be the line that touches the graph in one place around this area here. Okay, so I want you to get a picture of all this. And I especially want you to get a picture of this formula here. This is the derivative formula. Again, this is the foundation of the entire calculus curriculum, is this formula here. So now let's see how we can use this formula to find the instantaneous rate of change of the function at a point. In other words, the slope of the tangent line to a point on the graph. So we have a practice problem here. We're told that f of x is equal to x squared. So now we actually have a function to practice. to practice with, and we're told to find f prime of x. Now, what is f prime of x? Well, that is the derivative. That is the instantaneous rate of change of the function at some x value. So f prime of x is the limit of f of x plus h minus f of x all over h as h approaches 0. That's the definition of the derivative. So now we're going to find the derivative. We're going to come up with an actual function. So the easy part is to simply write h. Okay, h doesn't change. It never changes. Then we're going to write f of x. Well, f of x is just x squared. That's another easy part of this formula. So writing f of x and writing h are really easy parts of this formula. There's no tricks. But here's the tricky part. What is f of x plus h? What exactly is that? Well, f of x plus h is the exact same function that we wrote over here for f of x. They're not different at all. They're the exact same function. We have x squared. F of x plus h is going to be x squared. But instead of x, we write x plus h. Instead of x squared, we write x plus h squared. And of course, we have to write a subtraction symbol in between them. So now we have to find this limit, but thankfully in the previous classes we learned how to do that. If we just let h be 0, we get 0 divided by 0. You can verify that if you want to. Pause the video and verify that. You would just get x squared minus x squared over 0, which is 0 divided by 0. So we can't just let h be 0. We want it to be 0 because then we could find the slope of the tangent line, the instantaneous rate of change at some x value. But the problem is when we do that, we get 0 divided by 0. So we have to use some algebra tricks to find the limit here. So what we're going to do is expand the exponential expression. That's just x plus h times x plus h. You don't have to write that step because by now you should know how to do that. You can actually do that probably in your head. Of course, we're going to use FOIL. Some students may have learned the box method, but the box method is really not practical because you have to draw a box and it takes a while to do all that. So we're going to use FOIL. FOIL is the acronym FOIL, so we're going to multiply the first numbers. X times x is x squared. Then outside, that's going to be xh. And multiply the inside. That's going to be hx, which is the same as xh. And multiply the last term, so h times h is h squared. So very important to understand that all of this became that. Okay, so this is just basic algebra. So now you may notice that these x squareds actually cancel out. Also, we can add these terms. These are like terms. So we end up with 2xh plus h squared over h. Do you agree with that? Isn't it true, again, that these x squares cancel out? We've got a positive x squared and a negative x squared. And these terms, they may not look like it, but by the commutative rule of multiplication, these are like terms. You can just add them up and we get 2xh. xh plus hx is just 2xh, or you can write it as 2hx. So if we try to plug in h, or we try to plug in 0 for h, we still get 0 divided by 0. But as you can probably imagine, what we're going to do is we're going to factor out the h in the numerator. and you can see that the h's are going to cancel out. So now we're left with the limit of 2x plus h as h approaches 0. Before, we could not let h be 0. We want h to be 0 because then we can calculate the slope of the tangent line. But we couldn't do it up here because we get 0 divided by 0. But now we have this simplified expression, and if we let h be 0, at that point we get rid of the limit notation. We don't need the limit notation anymore if h is 0. Once we let our value be equal to whatever we're approaching, then the limit notation can disappear. So now we're left with f prime of x is equal to 2x. So that is what we're looking for. That's called the derivative. So we started with this function up here. That's f of x. F of x is equal to x squared. We found that f prime of x is equal to 2x. So it's important to understand what we just found. We found a function that we can use to find the instantaneous rate of change of the function at any x value. We can just choose some x value and plug it in, and the tangent line at that x value to the graph, we can find its slope. That's whatever 2 times that x value is. So in order to demonstrate, it says up here, draw the line tangent to the graph of f of x at x equals 1. So we're just using x equals 1 as an example. So if we move out 1 unit on the horizontal, or in the horizontal distance, then that corresponds to this point, right? That point has an x value of 1. So the tangent line is the line that just kind of touches the graph. It touches that point, but it doesn't touch any other points around that point. That is the tangent line, and the slope of that line is what we interpret as the instantaneous rate of change of the function at that point. Well, if we want to find the slope of that line, we can use the derivative function that we just found. We know that f prime of x is 2x. So if we want to find the slope of that green line that we just drew, we just plug in 1 to the function, and we have our slope. Just so happens the slope at that point is 2. You can kind of see that by looking at the graph. If you move out 1 unit to get to the line, you have to move up 2 units. So the slope is 2. But that's the instantaneous rate of change at this particular point. If we move the point up a little bit, then the slope changes. It actually gets bigger and bigger and bigger. So now let's find the slope of the tangent line when x is equal to -2. So now we have the same graph, same function that we're dealing with, but let's move out 2 units. The point on the graph that corresponds to that is this point up here. Actually, it should be this point here. My graph is not completely accurate, but it should be right around there. So the tangent line at that point is this line here. So that is the instantaneous rate of change of the function. The slope of the tangent line is the instantaneous rate of change of the function at that point. Now let's find what that change would be. So f prime of x we found is 2x, right? That's the function that we can use to find the instantaneous rate of change. Well, now we just plug in -2. So we get 2 times -2, which is -4. So it's negative because this line is going down from left to right. And it's a pretty steep line. That's why the slope is 4. So what that means is we go down 4 units for every 1 unit that we move to the right. So my graph is not drawn exactly. It's kind of hard to draw a perfect line, but what this means is that if we move 1 to the right, then we move 1, 2, 3, 4 units down. That is the instantaneous rate of change at that point, the instantaneous rate of change of the function. So do you see how useful that equation is? This equation can be used to find the instantaneous rate of change of the function at any x value. So let's do it one more time. Again, we're using the same function. We have this function over here, the f of x equals x squared function. And now we want to draw the line tangent to the graph when x is equal to 0. So that line would actually be flat, because the curve has what we call a minimum value. And so we're talking about this point here. We want to find the instantaneous rate of change of the function at that point, and that instantaneous rate is actually going to be 0 because the slope of the tangent line is 0. So let's confirm that with our derivative function. The instantaneous rate of change of the function at some x value is equal to 2x. In this case, we're plugging in 0 for our x value, so the instantaneous rate of change is 0. So this is differential calculus. It's finding functions that tell us the instantaneous rate of change of a function at some point on the graph, or given some x value. It's the slope of the tangent line through a point on the graph. Okay, now you're probably thinking to yourself, that was really difficult to find that function. We had to do a lot of math here. But the good news is that you're not going to use this math very much to find the derivative of a particular function. You're going to learn some quick ways to find the derivative of the function. And that's what we're going to be spending most of our time doing in this course. But for now, we just have to see how that formula is actually used, because again, it is the foundation of the calculus curriculum. So now we have a different function. Given this function, we're asked to find f prime of x, the derivative, which again represents the instantaneous rate of change of the function at some x value. So it's defined to be the limit of f of x plus h minus f of x all over h as h approaches 0. You need to have this formula memorized. So that's just for any function, f of x. But now we're identifying the function as root x minus 4. So now we're going to find the derivative for this particular function. Now again, the easy part is to just rewrite h. H doesn't change. And we're also going to rewrite f of x. That doesn't change. That's just root x minus 4. So those are the easy parts of the formulas, or this particular formula. I think I used orange last time. The hard part is finding f of x plus h. That's the part that really confuses students. Again, f of x plus h is exactly the same as f of x, no difference whatsoever, except instead of x, you write x plus h. So it's the exact, see, the purple is exactly the same as the yellow. The only difference is that we wrote x plus h instead of x. Again, this formula seems like a very, very complicated formula, but it's really not. once you get used to it, it's really easy. Now notice how I wrote parentheses around root x minus 4. If you don't do that, then you're going to get the wrong answer. You're subtracting f of x. The root x and the minus 4 are all part of f of x, so you have to subtract the whole thing, not just root x. If you don't write the parentheses, that means you're only subtracting root x, you're not subtracting negative 4. Those are the types of things that really make students stumble. It's the little details in math that really hurt students. Okay, so now we just have to simplify this expression and somehow calculate the limit. And of course, we learned our special techniques in the previous classes. First of all, let's get rid of those parentheses. So we have negative root x plus 4. And notice that these 4's cancel out. We have a negative 4 and a positive 4. So again, we're looking for the derivative of the function, which gives us the instantaneous rate of change of the function. So we're left with root x plus h minus root x all over h as h approaches 0. Now, if we let h be 0, because that's what we want, then we get root x minus root x over 0, which is 0 divided by 0. So we can't do that. Obviously, we have to use some special algebra tricks. So that's what we learned how to do in the previous classes. So now we have square roots, and of course we learned how to deal with this situation. The limit does exist, but we can't find it unless we do some algebra tricks. Now we have to write purple parentheses around that difference, or else it's not going to work. We're going to get the wrong answer. So we're going to multiply both sides of the fraction by root x plus h plus root x. It's got to be the opposite sign. So this is the fundamental principle of fractions. You can multiply both sides of a fraction by the same number, and the value of the fraction remains the same. So, in the denominator, we are not going to multiply. Remember, we talked about that in previous classes. We don't want to multiply, or I should say more specifically, we don't want to distribute. We just leave it in factored form. If you don't leave the denominator in factored form, then there's no way we're going to be able to find the limit. I guess we could still find it, but it would be more difficult to explain. Now we're going to use FOIL in the numerator. We have to use FOIL. So root x plus h times root x plus h is root x plus h squared, and you can jump forward with this. You don't have to listen to every single step of this. If you feel comfortable with the algebra, then you can just jump forward. But I'm just going to show students the algebra. So that was f of FOIL. Multiply the first terms, then we multiply the outside terms, and you can just write root x times root x plus h. You don't really have to combine those. You could combine them if you wanted to, but it's kind of a waste of time to do that. So now we're going to multiply the inside terms, negative root x times root x plus h, so that's minus root x times root x plus h. And then we're going to multiply the last terms. Negative root x times root x is negative root x squared. So I'm going very slow here. I'm showing every single step. Again, if you feel comfortable with the algebra, you don't really have to show every single step. You do have to show some work. A lot of students might get excited and say, well, I don't have to show anything. I can just write the answer. No, you have to show the work. You just don't have to show every single step that I'm showing here. So now the square root of x plus h squared is just x plus h, because squaring is the opposite of square rooting, right? Well, these terms, notice that those terms are exactly the same. This term and this term are exactly the same, except one has an orange negative symbol, and the other one has a blue positive symbol, so they just cancel out. And squaring is the opposite of square rooting, so again we just have x. So this expression over here became x, and this expression became x plus h. And then of course we just rewrite the denominator. We have h times root x plus h plus root x. So now the derivative is equal to the limit of h, because the x's cancel out. Notice that those x's cancel out. These x's here, they cancel out. X minus x is 0. So we have the limit of h over h times square root of x plus h plus square root x as h approaches 0. And if you want to, you can use brackets. Again, you could probably get away with not using brackets, but it's good to use those whenever you feel that there's any ambiguity. So now we're going to go up here, because we're out of room, and you see that these orange h's just cancel out. That's what we want. So then we end up with f prime of x is equal to the limit of 1 over the square root of x plus h plus square root x. So I'm going to move this over a little bit. So we have a little more room. So again, the expression is simplifying, and if we allowed h to be 0, that's what we want. We want h to be 0, but over here we would get 0 divided by 0. Now that the h is canceled out, we can let h be 0. And as soon as we do that, the limit notation goes away. So we have x plus 0 in that root, and then of course we have 1 over the square root of x plus the square root of x, because x plus 0 is just x, and you can combine those root x's and we're left with 1 over 2 root x. So that is the answer that we're looking for. That's the derivative. The derivative is a function which tells us the instantaneous rate of change of the y values of the function. Whenever you say the instantaneous rate of change of the function, you mean the instantaneous rate of change of the y values of the function in respect to x, or as x is changing. So that is the function that we can use. And so now let's use that function in an example. So it says here, draw the line tangent to the graph of f of x at x equals 2. So I'm going to move out 1, 2 units and find the corresponding point on the graph. Then I'm going to draw the line that is tangent to that point, tangent to the graph at that point. And what we're going to do is find the slope of that green line. That's very easy because we found the derivative function. If you recall, that was the answer to part 1 of the problem. So now they're asking for the the slope of the line that's tangent, the slope of the green line when x is equal to 2. So we just plug in 2, and we're done. This blue number here, that's the instantaneous rate of change of the function when x is equal to 2. It's the instantaneous rate of change of the y values when x is equal to 2. So, let's try another one. It says, draw the line tangent to the graph of f of x at x equals 4. So I'm going to move out 1, 2, 3, 4. Find the corresponding point on the graph, and then draw that tangent line. And then we're going to find the slope of the tangent line using our derivative function that we just found, which is 1 over 2 root x. We're going to plug in 4. So we have 1 over 2, the square root of 4, which is 1 over 2 times 2, which is 1 over 4. So that kind of makes sense because this line is not very steep. It's only got a rise of 1 for every 4 units of x. My line may not be exact, so if you try to find the slope and it doesn't look right, again, we're just our drawings are just estimates. They're not the exact. It's not exact, but you can see that it's close. The slope of that line looks to be maybe about 1/4. Okay, so let's try another problem. And again, we're using the same function. We have the same function, and we have the derivative. So we're going to find the slope of the tangent line. But first, let's draw the tangent line when x equals 1. So we're going to go out 1, x equals 1, and find the corresponding point on the graph, and then draw the tangent line, and now we're going to find the slope of that tangent line. So we're going to use f prime of x, which is 1 over 2 root x, but now we're going to plug in 1 for x. So we have 1 over 2 times the square root of 1, which is 1 over 2 times 1, which is 1/2. So my line looks like it has a slope maybe close to 1/2. So again, these lines are just drawn quickly, so it may not be exact, but that is the instantaneous rate of change of the function, meaning the instantaneous rate of change of the y values of the function when x is equal to 1. It's the slope of that green tangent line. So there's another problem where we found the derivative function. We had a problem here where we were dealing with the function f of x equals x squared. The derivative was 2x. If the function is x squared, the derivative was 2x. And here we had a function f of x is equal to root x minus 4, and the derivative was 1 over 2 times the square root of x. So let's do one more of these problems. So now we have this function here, and we're asked to find f prime of x. Well, f prime of x is defined to be the limit of f of x plus h minus f of x all over h as h approaches 0. And let's find the derivative for this particular function. So again, we're just going to rewrite h. That's the easy part. We just rewrite h, and then we're going to rewrite f of x. So f of x is just going to be 2 over x, because that's what f of x is. So that's the easy part. The part that students have trouble with is f of x plus h. Again, it's not difficult. F of x plus h is exactly the same as the yellow f of x. It's exactly the same. The only difference is, instead of x, you plug in x plus h. So it's very easy. It just looks complicated. So if we plug in 0, we get 0 divided by 0. If we plug in 0 for h. So how do we find the limit? Well, we have to use algebra techniques. We can use algebraic methods to find the limit. In a function, most importantly, we can find a function for the instantaneous rate of change. So how do we do that when we have a complex fraction? Well, we just simplify the complex fraction. And in order to do that, we have to combine the two fractions in the numerator. And in order to combine the two fractions in the numerator, we have to have a common denominator. So I'm going to multiply both sides of this first fraction by x. And when I do that, I have to use purple parentheses around the x plus h. I know you don't want to, but you have to. Then we're going to multiply both sides of the other fraction by x plus h. Why are we going to do that? Well, because now we have a common denominator. It's that simple. The denominators look exactly the same. So we get 2x over x times x plus h, and we're going to have to distribute here. 2 times x is 2x, and 2 times h is 2h. And that's all over h. I'll move this down a little bit. So now that we have a common denominator, we can go ahead and combine those fractions. So we have 2x minus 2x plus 2h all over x times x plus h, and all of that is over h. So it's very important to keep track of what fraction is inside what fraction, or else things can get really confusing really fast. So you want to make the upper fraction line smaller so we understand that this is a fraction inside a bigger fraction. Okay, so now we're ready to simplify the numerator. That negative just goes, well, it distributes. So we have 2x minus 2x minus 2h all over x times x plus h. You don't have to show quite so many steps. Again, I'm just showing the steps so you can know what's happening. So as you can see, the x's cancel out, or the two x's cancel out. So we're left with negative 2h over x times x plus h all over h. And at this point we can use our old school division. Remember, a fraction line can be interpreted as a division symbol. So that becomes negative 2h over x times x plus h divided by h. Now, when we're dividing, remember we can flip the divisor and change to multiplication. So we get negative 2h over x times x plus h times 1 over h. Again, we're going slow here so you can see what's happening. And so we multiply the fractions. Remember, when you multiply fractions, you just multiply the numerators. So negative 2h times 1 is negative 2h. And then multiply the denominators, h times h, or x. Well, it's a mouthful, but you can just put the x and the h next to each other. Alright, so now you can see what's going to happen. The h's are factors of the numerator and the denominator, so they're just going to cancel out. And let me find some more room. Okay, so the h's cancel out. And we get negative 2 over x times x plus h. And again, if we let h equal 0 up here, we get 0 divided by 0. But now, if we let h equal 0, and remember, when you do that, the limit notation disappears. Now, if we let h equal 0, then we get negative 2 over x times x, which is x squared, because x plus 0 is just x, right? So this is the derivative function. So to demonstrate, let's look at this graph here, and let's draw the line tangent to the graph of f of x at x equals negative 1. So we're going to go out negative 1 and then count until we get to the corresponding point in the graph, and then we'll draw that tangent line, and it'll look something like that. I'm going to make my marker a little thinner there. So that is the tangent line, and now we're going to find the slope of the tangent line using our function. We found that f prime of x is equal to negative 2 over x squared. So now we're going to plug in negative 1 for x, and that's going to tell us the slope of this tangent line, which is the instantaneous rate of change of the function when x is equal to negative 1. So we get negative 2 over 1, which is negative 2. Now again, my line may not be completely correct. It probably needs to be a little steeper. But we're just drawing the line just so we can get a general idea of what exactly we're finding. So now let's draw the line tangent to the graph when x is equal to 2. So we count out 1, 2, and then find the corresponding point on the graph. This line looks like it's not going to be quite as steep as the previous one. So now we're going to find the slope of that line, which again is considered to be the instantaneous rate of change of the function, or the y values of the function, when x is equal to 2. So we have negative 2 over 2 squared, which is negative 1/2, if you simplify that. So that makes sense because this line shouldn't be as steep as the other line. Okay, so we found the instantaneous rate of change of the function when x is equal to those two values. And let's do one more problem. We're going to draw the line that is tangent to the graph at f of x, or of f of x when x is equal to 1. So we're going to go out 1 and then find the corresponding point on the graph and draw the line that's tangent to that point on the graph. And how do we find the slope of that line? Well, again, we use the derivative. So f prime of 1 is equal to negative 2 over 1 squared, which is negative 2. So we found the instantaneous rate of change of the function, or the y values of the function, at that particular point, which is interpreted as the slope of the tangent line to the graph at that point. Okay, so that is differential calculus. I'm going to give you another chance to take a picture of all this stuff here. And you can take a picture of the first problem that we did. That's going to be very helpful to you. Take a picture of the second problem that we did. And take a picture of the third problem that we did. And now it's time for you to try. So I'm going to leave all this in the window. Go ahead and try number 4. If you get stuck, that's okay. But give it an honest attempt and use those screenshots that I gave you a chance to take, those shots that I gave you a chance to take a picture of. Problems 1, 2, and 3, they'll help you, especially problem number 1. And when you come back, we'll do it together. Okay, we're back. So my graph may not be completely accurate. Again, the point of drawing these graphs is just to give you an idea of what's happening, not to draw a completely accurate graph or a tangent line. So if you got that right, excellent. So I want you to try another problem like that. I want you to try number 5. Now for number 5, number 2 here that we did together, that's going to be very helpful. So if you get a picture of number 2, that'll help you with number 5. Again, if you get stuck, that's okay, but give an honest attempt. And when you come back, we'll do it together. Okay, we're back. So f prime of x is equal to 1 over 2 root x. So if you got that right, excellent. So that's the answer. That's the slope of the line tangent to f of x at x equals 3. Okay, so let's try another one. Let's draw the line that's tangent. Okay, so there you go. If you got that right, excellent. Okay, so now I want you to try one more of these. The problem that's really going to help you with number 6 is this problem. So take a picture of this problem. And I want you to do number 6. Number 6 is going to be a little bit more challenging, but let's see if you can do it. You might be able to do it, so don't give up. So try number 6. If you do get stuck, that's okay. But try number 6. When you come back, we'll do it together. Okay, we're back. And finally, we have negative 1 over x plus 3 squared. And that is the derivative. So if you got that right, excellent. Okay, so now we're going to use that derivative. It says draw the line tangent to the graph when x is equal to negative 2. So I'm going to count out 1, 2 units, which is equal to negative 1 over 16. Again, the slope of the tangent line is interpreted as the instantaneous rate of change of the function. So if you got that right, excellent. So we're going to learn a new word. When we find the derivative of a function, that's referred to as differentiation. This is the noun version of the word. The verb version would be differentiate. So when we find the derivative of the function, we differentiate the function. So that's an important word that we're going to use in calculus. It's also useful to note that in the study of calculus, we call any graph a curve, even if the graph is not curved. Even if we have a line, we just refer to the graph of the function as a curve, so just be aware of that. So now we're going to get some more practice finding the derivative functions, and I want you to try part 1, and then we'll do part 2 and 3 together of this next problem. If you get stuck, that's okay, but give an honest attempt, and when you come back, we'll do it together. Okay, we're back. So let's write the derivative formula. So that's the formula, and now we're going to find the derivative function for this function up here. So remember, the easy part is h. We can just write the h there. And also f of x is the easy part. We're just rewriting what f of x is. That's just f of x right there. But we do have to use parentheses. If you don't use parentheses, you're going to get the wrong answer because we're subtracting this expression. So now f of x plus h, that's the part where students typically have some trouble. So we're going to write the same exact formula that we wrote over here, but instead of x, we're going to write x plus h. So there you go. So this is f of x, and this is f of x plus h. So the setup is really the most important part. So let's double check, make sure we did everything correctly. Everything looks right, so now we have to simplify the expression and find the limit. So I'm going to expand this. If you expand using FOIL and then combine like terms, you get the following expression. And then I'm going to distribute the -3 using the distribution property, and then I'm going to distribute the negative, and we end up with the following expression. So let's continue to simplify. I'm going to divide this polynomial by 2, so we get x squared over 2 plus xh plus h squared over 2. And you can see that some of these terms cancel out. This term cancels out. These terms cancel out. And don't forget to write over h. So now we can factor out the h. Because these terms have a common factor, which is h. And we're left with the following expression. So let's double check, make sure we did everything correctly. Everything looks right. The h's cancel out. So I factored out an h from all these purple terms that were left over after we canceled the green and the blue terms. And the h's cancel out, so we're left with x plus h over 2 minus 3. And so now we can let h be 0. Once we do that, we can get rid of the limit notation, and we end up with x plus 0 over 2 minus 3, which is x minus 3. So that is the derivative function. So if you got that right, excellent. But now we're going to find the instantaneous rate of change of the function f of x when x is equal to negative 3. Or we should say at x equals negative 3. Time is not really involved. So this function that we found down here, that's the instantaneous rate of change. That's the slope of the tangent line when x is equal to negative 3. So all we do is just plug it in. So f prime of x, we just found, is equal to x minus 3. F prime of negative 3 is negative 3 minus 3, which is negative 6. So when x is equal to negative 3, the function is moving down 6 units for every 1 unit that it's moving to the right horizontally. Again, that's the instantaneous rate of change. For this type of function, this is a parabola. The rate is changing at every instant. So now we want to find the instantaneous rate of change of f of x when x is equal to 2. So again, let's just rewrite our derivative function, and we want to determine the instantaneous rate of change when x is equal to 2. So we get negative 1. So the function is not changing as rapidly as it is when x is equal to negative 3. So again, this is the same thing that we did in the previous problems. It's just we're using different terminology. We're calling it the instantaneous rate of change, whereas before we were just looking for the slope of the line tangent to the curve at some x value. Again, it's just the same thing. So I want you to try part 1 of problem number 8, and when you come back, we'll do it together. Okay, we're back. Let's write our derivative formula. It's good to keep writing this formula because it's the foundation of the calculus curriculum. It's important that you understand and remember that formula. So now we're going to find the derivative of this particular function. So let's do the easy parts first. H we just rewrite, and f of x we just rewrite. Alright, so f of x plus h, that's the hard part. Remember, f of x plus h is exactly the same as f of x. No difference whatsoever. Except, instead of x, we write x plus h. So this is f of x plus h, and this is f of x. So let's double check that, make sure we have it right. Everything looks good. So now we just have to simplify and find the limit. So we have negative 2 root x plus h minus 7 plus 2 root x minus 7 over h. And there's not really much we can do at that point. without using our special trick. Now at this point you probably wondered, do we multiply by this minus this, or do we multiply by the positive version of this plus this expression? How do we do this? Well, I believe that both of those methods would actually work. I think it's easier to just change this to a positive number, but you could make both of these negative and you would still get you'd still find the derivative function, but it's going to be easier just to deal with positive. So I'm going to make this first expression positive. I'm going to give it a positive sign. And the reason that both of those methods would work, changing the sign of this or changing the sign of this, is that the inner terms are going to cancel out. That's really what we want, is for the inner terms to cancel out. So let's double check, make sure we wrote everything correctly. Everything looks right. So now we're ready to multiply. Again, this is just a trick to change the form of the expression. So we're going to multiply these, and we end up with negative 2 root x plus h minus 7 squared. And then we're going to multiply the outsides. When you do that, the negative 2 and the 2, they multiply. You can make it negative 4. And you can write it however you want to write it. We can combine this in many different ways, but I'm just going to write the roots next to each other. Then we're going to multiply the inside terms. Again, we're using FOIL. 2 times 2 is 4. Then we have root x minus 7 times root x plus h minus 7. And then we're going to multiply the last terms, and we get 2 root x minus 7 squared. And I'm going to make some more room here. And that's all over h times 2 root x plus h minus 7 plus 2 root x minus 7. And by the way, one thing that you can do to make this easier is you can actually factor out a negative 2 out of the limit. But I don't want to... some students get kind of complicated when you do that, or they get kind of confused when you do that, so I'm not going to factor out the 2 out of the limit. But remember, we can do that. We can take a constant out of the limit. That's limit rule number 5, I believe, if I remember correctly. 5 or 6. So now, and I forgot to write a parenthesis there, so again, your instinct is going to tell you to multiply h using distribution, but you don't want to do that. That's going to make things, well, it's going to be difficult to find the answer. So now, as you can see, these inner terms cancel out. And this term here, well, we're going to have to use a rule that we learned. This is exponent rule number 3. If you want to look it up in my beginning algebra, or my intermediate algebra course, we learned exponent rule number 3. That just means that you multiply, or you raise 2 to the second power, and that gives you 4. So we have negative 4, and then you raise the root to the second power, because 2 is multiplied into the root, just like a is multiplied by b. Or I should say 2 is multiplied by the root. So you square both the 2 and the root, and when you square the root, it just gets rid of the root. That's the opposite of square rooting is squaring. And we have plus 4 times x minus 7 using the same logic. on this term over here. So that term turned into that, and this term turned into that. So this is kind of a big problem. It's a lot of math here. And we're going to rewrite that factor in the denominator. And then I'm going to distribute the -4. And then you see that these terms cancel out. And these terms cancel out. So we're kind of out of room on this page, so I'm going to move up to the next page. Okay, so then we're left with -4h in the numerator, and h times 2 root x plus h minus 7 plus 2 root x minus 7, and the h's of course cancel out, and we have -4 over 2 root x plus h minus 7 plus 2 root x minus 7, and now we can let h be 0. We couldn't do that before, but now we can. So we have -4 over 2 times root x plus 0 minus 7 plus 2 root x minus 7, and now we have like terms in the denominator, so we can add those up. And we get 4 root x minus 7 and the 4's cancel out, and we have -1 over root x minus 7. So that is the derivative function. So if you got that right, good. If you got stuck there, if you had some problems, that's okay. But why don't you try part 2 and part 3. When you come back, we'll do it together. Okay, we're back. So if we're going to find the instantaneous rate of change, we have to use the derivative function. And we just found that. It's -1 over root x minus 7. So now we're going to plug in 8 for x. And we get -1. So we got that right, good. For the next problem, again, we're just going to use the derivative function. You don't have to rewrite it if you don't want to, but I'm going to go ahead and rewrite it. So we just plug in 15, and we get -1 over root 8. And it's okay if you left it like that, but technically we're not really supposed to leave it like that. We want to pull out the perfect square. You can review this stuff in my intermediate algebra course or my beginning algebra course, and then we're going to multiply both sides by root 2. And we end up with the following. So yes, I was skipping steps there to rationalize the denominator, but again, that's something that you should know in the curriculum. If you don't know that, then don't hesitate to go back to my beginning algebra course, where we talk about roots. They may be referred to as radicals, so on and so forth. So if you got that right, excellent. Okay, try number 9. Number 9 is kind of a special problem because we have a linear function. So I want you to try part 1, but we'll do part 2 and part 3 together. So try part 1 of number 9. When you come back, we'll do it together. Okay, we're back. So here is the derivative formula. It's very important to remember this formula and rewrite it over and over and over again, and to show what formula we're using here. So the function that we're dealing with is 7x plus 5, that is f of x. And we're subtracting that. And of course h we just rewrite. F of x plus h is going to be the exact same function, except instead of x we're going to write x plus h. Okay, so we're going to distribute the 7. The 7x's cancel out, and of course the 5's cancel out. So we're left with 7h over h, but the h's just cancel out. So then we're left with the limit of 7 as h approaches 0. But that's limit law number, I believe it's 6. It's either 5 or 6, I don't really remember. So I'm going to go ahead and write 6 there, just so we know. If you didn't write the 6, that's okay, but the limit of a constant is just equal to whatever the constant is. So again, if you were to graph that, it would be a horizontal line at x or y equals 7, and as h approaches 0, if h is on the horizontal axis, as h approaches 0, the dot just approaches 7. If you want to think about it that way geometrically. So the rate of change of the function is 7. It's always 7. Doesn't matter what the x value is, but that's the way it should be, because this is a linear function, which means that the rate of change of the function is the same for all x values. So it doesn't matter what x value you plug in, you're going to get a rate of change that's equal to 7. Now part 2 and part 3 are maybe a little tricky. But let's see if you can figure out part 2 and part 3. I'll give you a hint. It's really easy. The answer is really easy. So go ahead and try part 2 and part 3. When you come back, we'll do it together. Okay, we're back. So our derivative function tells us that the rate is always 7. The rate of change of the function is always 7. So if you plug in 4, you're going to get 7. Same thing for f prime of -1. It's just going to be 7. So again, that's the special case when the rate of change of the function is constant. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And screenshot number 2, and number 3, and number 4, and number 5, number 6, number 7, 8, and 9, but don't go before you get your homework. Here's your homework, screenshot number 1, and screenshot number 2, and number 3, and number 4. But don't go before you get the answers. Here's the answers. Get a screenshot of those. And the last couple problems. So remember, if you don't do the homework, it's 100% guaranteed that you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.